start recording. What about now? Can you see the full screen? Because I pushed the button start recording. So the recording is in progress now. Someone even left our tutorial. It was top right. So good now. So now it's good. What is top right? I don't know. Maybe this. Oh, does it look better now? Very strange, very strange. I can't see my screen. That worries me. I see only very small image. It's current speaker view. Yeah, current speaker view, but maybe I don't need it. Okay, let's get back. Okay, it's time to start tutorial actually. So can you see the full screen or what? I'm still quite confused because I see very, very small image of my screen. Okay, it's time to start. Okay, so the topic of today's tutorial will be eigenvalues and eigenvectors of matrices. Let's write it down. Eigenvalues, and eigenvectors, eigenvectors of matrices. So my goal as a tutor is just to give you some algorithm, a clear algorithm as to how to calculate these guys, not going deep into details, because I myself listened to Sergey, your lectures yesterday, and they are absolutely good. They are absolutely wonderful. So you can find out all the necessary things, all the philosophy, all the concepts behind these things in the lectures. No problem about it. So our goal is just to learn how to calculate them in an efficient and fast way. Okay, so I prepared two problems for you to solve for today, two matrices. One of them is smaller one, 2 by 2, and another one is bigger and longer one, 3 by 3. And of course, the convention is usually to start off with simpler examples. But I decided to do it just the other way around, because by the end of the tutorial, everyone is a little bit tired. That is why I think it's a better idea to solve the more difficult, more challenging task before we are all a little bit tired. So let's start out with this, the first matrix. So the first matrix will be 3 by 3. So the first row is 0, 0, minus 2. The second is 1, 2, 1. And the last one is 1, 0, 3. It's not from your tutorial sheet, by the way. I took it from the study guide because I really liked the situation which happens in this particular problem. But of course, after this tutorial, you can solve all the problems from your tutorial sheet. They are pretty similar. It's just a warning. So there's no this task in our tutorial sheet. Okay, now it's start to solving this problem. So in the first big step, you need to calculate eigenvalues first. Eigenvalues. The vectors will come after. So how we usually do it? We need to compile so-called characteristic equation. Let's write it down. Characteristic equation. Characteristic equation of this matrix. How does it look like? The symbolic notation looks like this. So vertical bars, A is our given matrix, A minus lambda times identity matrix. Vertical bars are closing and all is equal to 0. So what does this equation mean? What's hiding behind this equation? So you know that I is identity matrix, the matrix which has ones on main diagonal and the rest of the entries are zeros. Lambda is our eigenvalue, which we are going to find. So this is equation with lambda being an unknown. And A, our given matrix. So it's pretty obvious that as a result, inside of this vertical bars, we have matrix of the same size, 3 by 3. And again, it means that vertical bars are not denoting absolute value, as one might think. It's just a determinant of this matrix. Sometimes people don't use this vertical bars, they just write det in front of this matrix. Okay, so what is the idea behind this matrix, which is inside vertical bars? It actually means that we need to subtract lambda from each diagonal element of the initial matrix. So we have three elements on this diagonal, 0, 2, and 3. And they will need to be turned into 0 minus lambda, 2 minus lambda, 3 minus lambda. Okay, let's do it. So I'm putting vertical bars immediately because it's determinant. So 0 minus lambda, 0 minus 2. That's how the first row will look like now. Then the second row, we need to subtract minus lambda from this element, from 2. 1, 2 minus lambda, 1. And the last row will look like 1, 0, 3 minus lambda. And again, it's equal to 0. So this looks like an equation already with only one unknown, lambda, which is our eigenvalue. But you know what? We need to start calculating this matrix. So the best way is to use expansion along some row or column. I'm choosing the first row because I really like it, because it has 0. It means that we are not going to deal with all the 3 terms in our determinant expansion, but only with 2, the first one and with the third one. So the combination usually goes like this. Go for the row or column which contains at least 1 0. Okay, let's start expanding. So the first element in this row is minus lambda times what? We need to cross out the row and column where this element is positioned now. So we are crossing out the first row, the first column, and as you can see, we are left with this 2 by 2 matrix. We need its determinant. So let's write it down here. 2 minus lambda, 1, 0, 3 minus lambda. Okay. The second element in this row usually comes next, but we ignore it because it's just 0. We immediately go to the second, to the last one, minus 2. Minus 2 times what? Again, we are crossing out the row number 1 and the column number 3 this time. And we are left with this matrix, 2 by 2. So 1, 2 minus lambda, 1, 0. And we are writing the quality to 0. Okay, now it looks a little bit better, of course, but still we need to calculate these 2 by 2 matrices, determinants, which is pretty easy. Okay, minus lambda times what? This guy, 2 minus lambda times this guy, which is 3 minus lambda. And luckily, we don't need to subtract 0. Of course, we can do it, but I'm too lazy to write it down. I think that you might be lazy too. Okay, minus 2, and this determinant goes like this. 1 times 0 will be 0. I prefer to write it down. Minus 1 times this guy, 2 minus lambda. We close in parentheses, and it's all equal to 0. Okay, so now it looks like quite a conventional equation without any determinants, without any matrix, just a pure equation. But you know what? The bad news is that it's cubic equations. And cubic equations are quite a hassle to deal with, to be honest. Maybe you vaguely remember the method, maybe from your high school, that you're supposed to guess one of the roots and then do the division. And so it's quite a long story. That is why the recommendation is don't ever try hard not to end up having a classical cubic equation. What I mean by classical, when you do all this multiplication, when you expand all these parentheses, you will end up having classical cubic equation. It's not a good idea. It's better to think in terms of factorization, this left-hand side from the very beginning. So here, I'm not going to touch the first term because I'm sort of afraid of it. I'm just rewriting it, minus lambda, 2 minus lambda. I'm delaying this until the very last step. But I'm quite unhappy with this big term. Look at this. It should definitely be simplified, cleared out. Look at this. 0 minus something looks pretty silly. We can do this multiplication. And in this case, it will be plus 2 times this guy, which is 2 minus lambda. Okay. Again, at this point, you might be tempted to do all this multiplication. Don't be tempted, because now you can clearly see quite a beautiful thing. Look at this. There are actually 2 terms. This is the first term of our equation, and this is the second term. And there is a sign plus instead in between. If you look at every term, you can clearly see that they do have something in common. They have this guy, which is 2 minus lambda, which could be used as a common factor. So we can pull out this common factor, write a new parenthesis here. And now what is left from the first term? We took away this guy, so we are left with minus lambda times 3 minus lambda. Then we can, so this is what used to be the first term. This used to be the first term. Now we can rewrite this plus sign, which is here, and then we are looking now at the second term. Second term, we just got rid of this guy, we pulled it out, and this is why we are left with 2 only, plus 2 equal to 0. So this is the best way to solve these equations. You might think that, oh, it's all material from high school, no problem about it. But it turns out this is actually the trickiest part of this problem. Sometimes you might get just stuck, considerably stuck, if you don't do it in a proper manner, if you don't try to factor out this common factor. So it's quite a tricky part, even though it is from high school, of course, no doubt. Okay, and now why this cubic? It's still cubic equation, but it's just such a wonderful cubic equation because it looks like like A times B is equal to 0. When how do we usually solve these equations? Very easily. So either I, the first term, is equal to 0, or either B is equal to 0. That's it. So it was a very clever move for us. To be able to factorize this equation. So now the first case will give us lambda is equal to, so this is our first eigenvalue already. And as for this equation, it needs some clearing up, but it's very easy. Minus 3 lambda plus lambda squared plus 2 is equal to 0. Now I'd better rearrange these terms. And we have a quadratic equation now. Of course, everyone knows how to solve it. You remember this word discriminant and everything. So it will be 3 plus minus discriminant is 9 minus 8, so 1 divided by 2. And finally, we have 2 more roots. If plus sign corresponds to which? To 4, and minus sign corresponds to 1. So it looks like we have 3 equations, or 3 values, 3 roots, which is quite natural because we are dealing with a cubic equation. But very strange. These two roots actually coincide. We got 2 twice. It doesn't mean that mathematicians prefer to say that we have 2 roots, but some. Yeah.
I think it's actually -2, -1.
Really? Why?
Because lambda is -3, so it would mean -2, -1 is -3 lambda. -2 times -1 will give you -2, plus 2.
No. You're speaking too fast for me. Sorry. So, do you agree with this equation, the second one?
No, don't. Just the second last step.
Second last step, this one.
Yes. So that there is -2, -1 will give you lambda.
No. This should be 3 here, according to the formula. And you can always check your result, by the way. Very good question. You can, if you have some doubts about me, about yourself, you can always check. Look at this. Let's take the first root, 1, and let's try to substitute into this equation. This is the best way of checking. So 1 minus 3 will be -2 plus 2. No, it holds correct. Okay. So, no, it's not about the majority of people getting the same answer. The majority of people can be wrong as well. So it's always a good idea just to check. Yeah, somehow I myself have doubts. So please, you're welcome to ask more questions. No problem at all. Okay, so let's just write down our result. So we have actually 2 roots instead of 3. So lambda 1 is equal to 1. It's just an ordinary root, nothing special. But lambda 2 is equal to, it's called a repeated root. Mathematicians prefer to say that it's a repeated root. But it doesn't matter so much, to be honest, for our today's tutorial. You just have 2 or 3 roots. It doesn't matter. The quantity doesn't matter, because we need to proceed to the second step, which is much bigger. It turns out that every eigenvalue has its own eigenvector, or even vectors. Some eigenvalues can give birth, or how to say, to even several eigenvectors. So let's switch to this next step. Okay, I'll start out with the first root. So let's take our first eigenvalue. I need the full screen now. So the first eigenvalue is lambda 1 is equal to 1. How to calculate eigenvectors? Is there an equation or method or something? Yes, and the answer is yes, there is an equation, and I'm going to write it down in the general form, of course. Okay, look at this. A minus lambda times identity matrix. Very familiar expression. We already used it during our first step. Do you remember? It was characteristic equation here. So I'm actually using the same matrix, but this time the difference will be that I'm using matrix notation. It won't be determinant anymore. It will be matrix, real matrix. And another difference is I put here index y, subscript I, because by lambda I, it means that we are using now the current lambda. We have two lambdas. We have choice of lambdas. And so I mean that for current lambda, it can be lambda 1 or lambda 2, I'm using its own particular equation. So what next? Times our eigenvector, ARY again. And it's all equal to 0 or 0 matrix, rather, 0 matrix. So this is the general equation which allows you to find eigenvectors. Eigenvectors are our goal from this equation because we already know everything. We know matrix A from the very beginning. We just calculated lambdas. We need to substitute them. So this would be quite a good matrix. But this is unknown vector, eigenvector AI. But you know, this equation looks pretty nice, but it's like in a very concise form. We'd better expand it as much as possible to have a better idea what's behind it. What is this matrix? We just discussed it before. It means that lambda I gets subtracted from every diagonal element from matrix A. So what? And I already wrote down this matrix actually. Look at the first step and the previous page. So this is actually the matrix which is inside, which we need to use now. So what I'm going to do, I'm just going to rewrite it from the first page and put it here. Okay, so it will be minus lambda 0 minus 2. I'm just rewriting it from the first page. 1, 2 minus lambda, 1, and finally 1, 0, 3 minus lambda. The only difference, I need to put this lambda I, lambda I, lambda I. Okay, so this is substitution instead of this matrix. Then as for eigenvector, it's just a vector with unknown components x, y, z. So the dimension of this vector is 3 by 1, because the initial matrix was 3 by 3. And finally, the right-hand side will give us a vector, again, 0, 0, 0. Okay, so this is the general equation with which we are going to deal with when calculating, when finding these eigenvectors. Okay, but you know what? Maybe you immediately realized, looking at this, this equation, that it's actually a matrix form of system of linear equations. Quite a familiar guy. We discussed it so much. We discussed them so much during our last tutorial. Previous one. So how do we usually solve linear equations? We write them in the matrix form, which is already here, and start applying Gaussian elimination method. So I don't think that anyone fancies writing down this system of linear equations. I think that we'd better start dealing with this matrix immediately. But all we need to do, we need just substitute our lambda I with current value, which is lambda 1 is equal to 1. So I'm writing down this matrix now. So I'm writing 1 instead of lambda. Minus 1, 0, minus 2. The second row is 1, 1, 1. Very nice. 1, 0, 3 minus 1 will be 2. So this is the matrix of coefficients for our system of linear equations. And all we need to do now, we need to recall this algorithm. Do you remember we used Gaussian elimination method last time to bring this matrix to so-called row echelon form, which means a triangle of zeros here in the bottom left corner. After this, we found leading elements, and leading elements allowed us to determine which variables are free. We denoted them by letter T or maybe T1, T2, and so on. And after that, we were ready to write down the solution of the system. And after that, okay, so let's do this process once again. But you know, the very first requirement is that we need +1 here usually. It's much more convenient. So how to provide +1 here instead of 1? We're allowed to do 3 row operations, and one of them is multiplying the whole row by some constant, not zero constant, of course. So what we can do, we can multiply the first row by -1, and we immediately get a 1 in this top left corner. It's just convention because it's very, very convenient. But I need to rewrite the rest of the rows now. Okay, so couldn't you just swap the? Yeah, it's another good idea. I would be able to get the same result if I swapped the first row with the second or maybe the third one. So you are free to do it in your own way. But remember that you are allowed to do only 3 operations and only on rows. This is just a big requirement. Okay, now it's time to apply our Gaussian elimination method. Do you remember? You need to remember just goal. So the goal is to get zeros here on the first step using the first row only, because we have a 1 here. What is this? -2, 1, 1? What are you saying? I don't quite get your idea. Vector. Oh, this one. I feel confused. I can't understand your question. What's wrong? What do you think is wrong? Maybe no, so everything seems to be correct. Okay. I think he's saying the answer. Really? Oh, no. I'm going to spend quite a lot of time on it because I need to explain it to you. Okay, so the first step is about getting rid of this guy. I mean, turning them into 0 using the first row only. And the second step would be about getting rid of this guy using the previous row only. I got the same. Okay. Just reading. Okay, so let's start doing it. So let's get down to the first step. We need to get rid of this and is. Yeah, I know, but I'm trying to, people saying that you can easily solve it just as it is. You know, the problem is that I want to show you that every single task can be done in a similar way, in the same algorithm. It's a very valuable knowledge because you will never get lost. Sometimes the situation might be quite untypical and you might get lost. But if you are armed with a very reliable algorithm, which has the same steps all the time, so you will be you will feel more confident. That is why I try to follow my algorithm all the time, even for the simplest tasks. So this is the goal. Of course, if I had to solve these equations for myself, I would do it in a different way every time. But when I tell this algorithm to people, I need to follow the same procedure all the time, because otherwise some people might get really confused.
In an exam or a test, are we allowed to skip that step in order to
Yeah, of course,
save time because we're under time pressure?
Yeah. If you are absolutely sure of yourself that you'll never make a mistake, you are allowed to do this. Of course, no problem, of course. Okay, so let's start doing this. So to get rid of this first one here in the second row, we need to multiply the first row by -1 and add it to the elements in the second row. And I forgot to mention that the first row should be rewritten just. It's already finished. Okay, -1 plus 1 will be 0. 0 plus 1 will be 1. And -2 plus 1 will be -1. Okay, now it's time to proceed to the third row. But luckily, we are very lucky, you know, because we already have a 1 here. And again, to use the first row, we need to multiply by -1, and everything is prepared here. So -1 plus 1 will be 0. 0 plus 0 will be 0 again. And -2 plus 2 will be 0 again. As you can see, we were prepared to proceed to the second step now, but it turns out we don't need it because it's already row echelon form. All of a sudden, the whole third row turned into 0 row. Quite a nice news. We don't mind having less work. Okay, what next? Next step is to find so-called leading elements of each row. So you look at each row at a time. You look at one row at a time, moving your mouse from the left to the right. And the first non-zero element in this row will be called leading element. So we look at the first row, but we are very lucky. The very first element in this row is leading element as well. Oh, very bad color. I need something like this. Okay, but as for the second row, we have leading elements 1 here, and no leading elements in the third row. So that's it. We found all the leading elements. After that, what we need that? Then we look at this matrix again, but this time from a different angle. We look at this matrix in terms of columns this time. So remember that the first column corresponds to X, the second Y, and Z is about the third column. And now we are looking at the column which doesn't contain any leading elements at all. So as you can see, it's only the third column which doesn't contain any leading elements which are circled in blue. That's what we are looking for. What does it give us? Okay, I need to switch to the next page, unfortunately. How to organize it? I need this matrix to be still in view. Looks pretty fine. Okay, so it means that Z is a free variable. Z is free variable. And in this case, we denote Z by parameter T. So Z is equal to T. After that, it's time to get back to our linear system. So this matrix actually is a representation of linear systems, of linear equations. And now it's time to rewrite every row like an equation. Oh, very bad image. So the first row has coefficients 1, 0, 2. What does it mean? It means that it could be written as a equation x plus nothing plus 0 plus 2z is equal to 0. So this is the equation corresponding to the first row. And the second row looks like 0, 1, minus 1. It represents equation y minus z is equal to 0. That's it. Because the third row is just zeros. It means that the third equation just disappeared in the process. Okay, now it's time to recall that we just denoted z as t. Let's use this notation and rewrite our equations again. X plus 2t is equal to 0, and y is plus y minus t, is equal to 0. And now, what is the convention? The convention is to leave basic variables. I forgot to mention. This way would take far too long. Yeah, of course, but you know, with time you will get used to this system. So I recommend you to watch my method first, and then and then you can watch some other tutorials or the lecture by Sergey, and you will compare and you will find out maybe the golden golden medium between them. Because I'm giving you the most reliable method, which will always work, even though sometimes it looks quite long. But you know, with time, if you solve like 5 or 6 problems like this, you will gain a very amazing speed. It's fine for you. I didn't have time to read it. It disappeared. Okay, so I forgot to mention that there are 2 kinds of variables, free variables and basic variables. So the convention is, as to how to solve these equations, to leave basic variables, which is x and y, to the left-hand side and bring the other guys to the right. So x will be equal to minus 2t and y is equal to t. So it looks like we finished. And now it's time to write our solution, which is vector with components x, y, z. Let's substitute our results here. Instead of x, we can substitute minus 2t. Instead of y, it's t. And z was denoted by t. After that, we usually pull out this common factor, which is t. And we are left with this result, minus 2, 1, 1. So we solved our problem. And at the same time, we got our first eigenvector. So this is our eigenvector. The convention is to put this parameter t in front. Even though some people prefer to write a vector as a column, this column, but it's better to put t in front to show you that this eigenvector is not unique. If you give some value to this t, you will get a new eigenvector. So it's better to put t in front. This is a requirement of our lecture at last. So this is why it's better to keep it. So our conclusion is that for eigenvalue 1, we have this eigenvector, which is t times this column, minus 2, 1, 1. So we are finished with the half of the task. Now it's time to do the same for the second. So for the second eigenvalue 2, you might say that maybe it's not needed because it will involve the same operations. But you know, the reason I chose this particular problem, because no, this process will be a little bit different, and that is why I don't mind spending some time on it. Okay, so now we are started dealing with the second lambda. Do you remember it was a repeated root? Lambda is equal to 2. Okay, we can use the same system, and the only thing we need to do, we need to substitute lambda I this time with our current value, which is 2. So let's write down the system. Okay, it will be I lost it. Okay, -2, 0, -2, 1, 2, 2, 2, 1, 0, 1, and 1, 0, 3 minus 2, 1 again. Looks pretty nice. The matrix of the system looks pretty nice. And of course, as usual, we want to have 1 here. It could be done in 2 ways, as you noticed before. I prefer to divide the whole first row by -2. 1, 0, 1. As a result, this matrix looks quite funny. All the 3 rows look pretty similar. And of course, but I prefer to pretend being a robot, sort of robot. Even though matrix looks so beautiful and you are tempted to solve it maybe in a quicker way, but nevertheless, I want to show you that this algorithm is so reliable, you can always rely on it. Because some people might get about such a beautiful matrix, but others, on the contrary, might be getting lost as to, oh, what shall I do with this matrix? It looks so unusual. It's better to follow your algorithm. So our algorithm is the same all the time. Get zeros here during the first step and get zeros here during the second step. It will always work. It will always give you a good result. Okay, let's start. So as usual, we are rewriting the first row, 1, 0, 1. And after that, it's time for this guy to disappear. So we need to multiply the first row by -1 and add the result to the second row. And it will give us 0, 0, 0. Very nice. And again, we are well lucky with the situation, the third row, because we have the same element 1. So we can use the first row multiplied by -1 again. And of course, these are too many words. The result, we get the result pretty quickly. So it doesn't harm you if you prefer to use algorithm instead of getting back to equations immediately. Look at this. It wasn't a lot of work involved, so it's okay. So now we have a row echelon form, and as you can see, we have only one leading element in the first row, which is not such a bad news at all. Maybe it's good. But the situation looks a little bit different to the previous one. You know why? Because this time we have 2 free variables. Look at this, 2 columns without leading elements. This is definitely something new. That is why I was so eager to explain you this particular problem, because this situation sometimes happens and you might get lost. Okay, what does it mean? It means that y and z are free variables this time. We have 2 of them. And how do we denote them? Y gets denoted by like as t1, and z is equal to t2. We need to use like 2 parameters. After that, we need to get back to our system, which is actually only the first equation, because the second and the third row just disappeared. Okay, quite nice. We don't mind it. X plus 0, x plus nothing plus z. X plus z is equal to 0. This is the only equation which is left of our system. And of course, we can now remember that z was equal to t2. And after that, our only basic variable, which is x, should be left in the left-hand side. And that's it. We solved our system. Now we are going to write down the answer, the solution, which is a column as usually x, y, z. And let's substitute our results here. So instead of x, we can substitute minus t2. Instead of y, we have t1. And instead of z, we can write t2. And maybe you remember our last tutorial, which was exactly a week ago in the lecture here, that I gave you a very strange example. I was explaining to you Gaussian elimination method, and one of the examples was very strange. I promised to give you the system of linear equation, but it was actually only one equation. So this is just the exact situation which I gave you last time. So, and the answer looks just like this. We had 2 parameters there. And what is the standard form of writing out this answer? It turns out that you need 2 terms. So one term will be coefficients in front of t1, which is 0 here. The second row gives us 1 and 0 here again, because there's no t1 here. And the second term will be about coefficients in front of t2. This is minus 1 here, no 0 here, and 1 here. Okay, so this is a standard form of representing your answer, your solution. And of course, we also found our two eigenvectors. So this is going to be vector I2, and this term is going to be vector E3. So you can see quite a curious thing now. Oh, sorry, shifting. So for eigenvalue lambda is equal to 2, we have even two eigenvectors, E2 and E3. These things sometimes happen. So it's quite normal. That is why I wanted to give you this particular example, because it contains such a unusual case, maybe in some way. Because all the problems which are given in your tutorial sheet, they have the same situation all the time. Every time for each particular eigenvalue, you get only one eigenvector, and after solving such problems, you might get the wrong impression that it's always true. No, sometimes situation evolves like this. Okay, so we are finished with this big problem. And I also want to highlight once again that the trickiest part of all this problem was actually in the very first step, when you are dealing with this cubic equation. Please try to be very concentrated at this point, because it's an absolutely terrible idea to do all this multiplication, because you will end up having a cubic equation, and it's an absolute nightmare to deal with cubic equations, especially during exams or tests. They are quite time consuming. So try to factor out these things. And this is why I would strongly recommend you to do all the problems from the tutorial sheets, just to get this practice, because it's really valuable practice, even though it sounds like from high school material. No, it's very, very interesting. I can assure you. Okay, so now it's time to relax. Now I want to give you having trouble factoring the 1 in 1C on the 1C, really? Yeah, I remember this. Maybe, I'm not sure. 1C, 1C, 1C. I need to have a look at it. Oh, I lost my tutorial. I'm not okay, what shall I do? I don't know. I don't have time for it. Okay, I have an idea. I have a solution. So I'm going to explain you this 2x2 matrix first. And then if you have some time left, I can explain you this 1C, okay? Okay. So let's solve another problem, which is much easier. Cool, thanks. Okay, nice. So this is matrix from your tutorial sheet this time. I think it's 1A, the very first one. It doesn't matter. So it's way, way easier. We need to perform the same steps, the same algorithm, but all these technicalities will be much shorter, much easier, much quicker. So we won't even spend much time on it. Okay, let's start. Do you remember the first step was to build characteristic equation, which looks like this again. A minus lambda times identity matrix is equal to 0. Actually, it means that we need to subtract lambdas from a diagonal element, and it will immediately give us matrix equation like this. So this is already characteristic equation, and no problem expanding this determinant, just a piece of cake compared to the previous one. So 4 minus lambda times 1 minus lambda plus 2 is equal to 0. And this is just a quadratic equation. You don't need to bother about factorizing or something. Just, do multiplication. It's the easiest way. 4 minus lambda minus 4 lambda plus lambda squared plus 2 is equal to 0. And finally, lambda squared minus 5 lambda plus 6 is equal to 0. Now we're applying this famous formula for quadratic equations root. 5 plus minus 1 again divided by 2, and we immediately get two roots. The first root is 3, I suppose, and the second is 2. So compare how much time we spent last time dealing with this characteristic equation and how easy it looks now, just out of comparison. Okay, so we already have eigenvalues, piece of cake. And the same is true for eigenvectors. Again, You can solve this problem of finding eigenvector in a more efficient, maybe a quicker way. But my goal, again, I'm saying it for the third time probably. My goal is to give you very reliable algorithm, even though sometimes it looks very long. I would recommend you to start to solve several problems applying my algorithm, which is a little bit long maybe. But after that, when you get bored with it, or maybe with some moments, you can another page. Yeah. Sorry. So the second page was about the first step, as you can see. I subtracted lambda from each diagonal element, and then I'm solving the resulting equation. So nothing new for you, actually. Nothing. Okay, so now it's time to find eigenvectors. Okay, so as you remember, we have special equation for these eigenvectors, which looks like A minus lambda I this time, which means current value. Identity matrix times our current eigenvector, which is IN, and is equal to 0. Again, it's better to rewrite this equation in a more, detailed way. So this, sorry, I'm getting excited probably because I'm running out of time a little bit. Okay, so we already have this equation in the previous page. Look at this. So this guy inside this vertical bar is actually the matrix we need now. So I'm just rewriting it onto this page. It will be 4 minus lambda minus 1, 2, 1 minus lambda. And the only difference is better to put I here. Then our eigenvector will have only two components this time, x and y. And finally is equal to vector 0, 0. That's it. Oh, I almost dropped my camera. Okay. So let's start dealing with this first lambda. So lambda 1 should be substituted here, which is 3. So we will have matrix 1 minus 1, 2 minus 2. As you can see, very small matrix. But again, you can apply the same algorithm. Why not? So our algorithm says that in the first place, you need 1 in the top left corner. We already have 1. And the first step and the only step will be to get rid of this guy using the first row as usually. Okay, so we need to multiply the first row by minus 2 and add it to the second row. And the first row remains the same in the process. So let's start. Minus 2 plus 2 will be 0, of course, and 2 minus 2 will be 0 again. So we are finished. This row Gaussian elimination looks very short here. No problem at all. It doesn't hurt much, to do Gaussian elimination. Okay, after that, we are usually looking for leading elements for each row. No problem again. We have only one leading element. And if you remember, the first column is about x, and the second column is about y. And after that, we are looking for a column without leading elements, which is the second column in our case. And it points out to the corresponding variable. So it means that y is free variable in our case, free variable. And we can denote it by t. Denoted by t. Immediately after that, we can get back to our system, which is actually one equation only this time. So 1 minus 1 corresponds to x minus y. X minus y is equal to 0. Now we have t instead of y, x minus t, and now we can solve for x. X is equal to t. And the solution will look like a column of two components only, this time x, y, because it's two-dimensional task. X is equal to t, y is equal to t again. We pull it out, this t, and this is our eigenvector already. Eigenvector, which is E1. Let's write it down. So for lambda 1 is equal to 3, for this eigenvalue, we have eigenvector t times 1, 1. That's it. So I don't think this process is quite long, but some people prefer to do it even in a more efficient way. I don't want to confuse you, but I just want to point you out that I myself don't do this long multiplications. I do it in a more efficient way, because always when you deal with matrix 2 by 2, these two rows sort of repeat each other. The fact that one of them disappeared, turned into 0, 0, it means that equivalent to saying that this row, second row, was the repetition of the first row. That is why what I'm doing usually, I just immediately get back to the equation, which is x minus y is equal to 0. And then, so it means that x is equal to 0. And I just try to put some numbers here. So for example, if y is equal to 1, x will be equal to 1 as well. So x is 1, x will 1, and I immediately get this eigenvector 1, 1, and I put t in front just for for correctness. That's it. You can do it in this much simpler way. I just wanted to show you this algorithm is applicable to any situation, absolutely any situation. It will always rescue you in some desperate cases. Okay, so I think that no one minds if I go for the next, for the second eigenvalue, which is, I don't remember it. It was 2. It was 2 in this problem. Sorry, I need to. So in this case, this general matrix, which contained a lambda I, we need to substitute 3 there. So it will be 4 minus 3 will be 1. So it will be, sorry, I need the black color. So 1 minus 1, 2 minus 2. Again, you may immediately notice that these two rows are repeating each other. So the second row is just a linear combination of the first row. That is why something is really suspicious. I know, I made a mistake. Because I was supposed to substitute 2 instead of lambda y. And I substituted the old number 3 again. I made a mistake. So 2 minus 1, and this will be minus 1. It's better to rewrite it. So 2 minus 1, 2 minus 1. So that's how the matrix looks now. Sorry, I was in a hurry. That is why I substituted the previous eigenvalue 3 again. Okay, now you can clearly see that these two rows are repeating each other. That is why you can use this shortcut, which is not about dealing with algorithm, not about row echelon form. You can just use the very first equation. Let's do it. Let's do the second eigenvector in a different way. Okay, so you can just rewrite this as a equation, ignoring the second one because this is one, and just find the numbers which would satisfy this equation. I think the most and these numbers should preferably be integers. So if you put x is equal to 1, for example, you will get y is equal to 2. And this is going to be our eigenvector. So x is equal to 1, 2, but t in front. So this is our second eigenvector, I2. So for lambda 2 is equal to 2, we have eigenvector E2, which is 2 times 1, 2. So what I did in this short problem, 2 by 2 problem, I found the first eigenvector I1 using my conventional algorithm, which looks a little bit long, but very reliable. And as for the second eigenvector, I used a shortcut way. I did it much quicker, much faster. But remember that this shortcut way is very clear only for matrices 2 by 2. But when it comes to matrices 3 by 3, as you saw from this big example, the situation can be really tricky. We had quite different situations for our two lambdas. The first one had only one free variable, but whereas the second one had two free variables. And that is why when you're dealing with matrix 3 by 3, the situation might become very tricky, and that is why this algorithm is the best approach to this situation, in my view. At least myself, I always use this algorithm when I'm dealing with matrices 3 by 3, because I feel that it's much more reliable. And if you solve, like, I don't know, 4, 5, or 6 problems like this, you will be amazed at your speed. Your speed will increase considerably. You won't mind dealing with this algorithm at all. Sorry. And now it's time to try and answer your question. I lost my tutorial sheet, to be honest. I don't have it at hand now. But it seems like I written out this matrix 1C. Please check me. Is this 1C or not? Plus 1 should be here. I want to give you the very beginning of this talk. Please. It's off the screen. Yeah. Sorry. So please check. Is this problem 1C from tutorial or not? Because I'm not sure. I put this tutorial sheet somewhere. I can't find it. I don't have it at hand at the moment. Really? Okay. I'll take it. So it's 1, 0, 4. It disappeared. I need to open the chart. How to open it? It's here. I had difficulty to. It's funny. 1, 0 minus 4, 0, 5, 4, and the last row is minus 4, 4, 3, right? So this is this is 1c. Of course, as I told you before, the trickiest part is to deal with this cubic equation. Sorry, I'm moving my camera all the time. Okay, so let's try and do it. The first element will be 1 minus lambda, 0 minus 4. Then the next row, 0, 5 minus lambda, 4. And the last row will be minus 4, 4, and 3 minus lambda. And it should be brought equal to 0. Again, it's better to use the row or the column which contains at least 1 0. I think that the first row maybe is a good solution. By the way, if you get again completely stuck, if you expanded your determinant 3 by 3 and you just got stuck, you can start these stacks all over again, expanding by some different row or column. Sometimes it works. But now I determined to do it this way. So 1 minus lambda times this determinant which is left after crossing out the corresponding row and column. So it will be 5 minus lambda, 4, 4, 3 minus lambda, and then we move immediately to minus 4, 0, 5 minus lambda, and here we have minus 4, and 4 in all this guy is equal to 0. I hope it's in the field of view. Okay, now it's time to calculate these determinants. I need more space, I need to make my handwriting a little bit smaller. 1 minus lambda. I prefer to use brackets actually to make things look clear. Okay, 5 minus lambda times 3 minus lambda minus 16, brackets are closing, minus 4 times what? 0? 0 minus this. Oh, quite tricky. I'm afraid to make mistakes. 0 plus 4 will be plus 4 times 5 minus lambda. Sorry, I'm running out of space. Is equal to 0. So it looks like it's quite right. Okay, this time it's again the situation is like we need to clear up this this place, and maybe we do some slight multiplication here. I mean that we can expand only these brackets, Okay, let's try to do it. 1 minus lambda. Yeah, it's a tricky spot. I agree. Even though it's cool material, but it doesn't mean that it's very easy. Minus 16, 1 minus lambda, and here we have minus 16 times 5 minus lambda is equal to 0. As you can see, the situation looks much trickier now. Yeah, last time we had only 2 terms. The first term was quite big one, and the second one was pretty obvious. But this time something really bad happening here. You know what we can try out? We can try, doing this multiplication. Maybe we will find some like terms, and they will give us maybe something good, but maybe not. Nothing is guaranteed. You will never know. We can just try if you don't run out of time, of course. Okay, so I'm rewriting the first term, and now I'm just doing this multiplication. It will be minus 16 plus 16 lambda minus 80 plus 16 lambda is equal to 0. Again, now I need to find like terms. Let's have a look at this this term. So these two guys will give us plus 32 lambda. I'm not rewriting this one because I'm saving my effort. And this will be like minus, these two guys will give me minus 96, if I'm not mistaken. Yeah, I'm not mistaken. I need a new page, okay? More paper. So I'm dealing only with the second term to reduce time and effort and so on. So can we bring out something? Yeah, we can bring out plus 32, and we are left with lambda minus 3. Good news, by the way, guys. Look at this. My handwriting is not very neat. I'm going to rewrite now everything. So the first term, 1 minus lambda, 5 minus lambda, 3 minus lambda, okay? And the second term, it's time to rewrite it. Plus 32 lambda minus 3 is equal to 0. So this is our result after so much suffering, I would say. So I hope you can clearly see it. And again, we look at these guys in terms of 2 terms only. This is our first term, and this is our next term. they do have something in common. Look at this. Here we have 3 minus lambda, and here we have minus, the opposite side, lambda minus 3. It means that this term should be prepared a little bit. If you pull out minus sign minus 1 from here, you will end up having the same expression, 3 minus lambda. Let's do it. So again, I need to rewrite the first term, which is a little bit annoying, but what can you do? And now we need just to pull out minus. It will be minus 32, and we can rewrite this 3 minus lambda, and that's it. Now you know what to do next. You have this first term, you have this second term, and they do have common factor, which is 3 minus lambda. So the situation is just like our big problem today. So that's it. I don't need that you will need any further explanation. That's it. We already passed the most difficult part. So I hope you're quite happy with the answer, with my explanation. Yeah, good. So I want to reveal you some big secret. All the problems which are given to the students, they look like this. They were a little bit adjusted, sort of adjusted to students, so that you could always find the solution factorizing out some common factor. So let this thought be inspiring for you. They are not going to give you some terrible, characteristic equations which will require, very long solution. No, they are all adjusted so that you could always find this common factor. Okay, so it's time to wind up probably, because you are having the next tutorial or next lecture. I don't know. If you don't have any question though, does anyone have some questions to me? No, it looks like everyone is silent. Okay, you're welcome. Thank you. Welcome. Okay, so see you next week, guys. And I recommend you to go through all these problems, by the way, in the tutorial sheet, because you do need to acquire some practice. You need to learn how to solve these problems more or less in a speedy way. There's nothing very difficult about it. It's all about speed, of course. Okay, so see you. I'm leaving now. Bye-bye. See you next week.